So let's look at example 5. A cosmetics company fills its best-selling 8-ounce jars of facial cream by an automatic dispensing machine. The machine is set to dispense a mean of 8.1 ounces per jar. Uncontrollable factors in the process can shift the mean away from 8.1 and cause either underfill or overfill, both of which are undesirable. In such a case, the dispensing machine is stopped and recalibrated. Regardless of the mean amount dispensed, the standard deviation of the amount dispensed always has value 0.22 ounces. A quality control engineer routinely selects 30 jars from the assembly line to check the amounts filled. On one occasion, the sample mean is 8.2 ounces and the sample standard deviation is 0.25 ounces. Determine if there is sufficient evidence in the sample to indicate at the 1% level of significance that the machine should be recalibrated. All right, so let's first look at what our null hypothesis is. This machine is supposed to fill everything to 8.1 ounces. So our null is going to be that status quo of what it's supposed to do and has always done in the past. All right, so our null hypothesis is that the mean is 8.1. All right, now we care if it's anything different from 8.1. If the machine underfills or the machine overfills, we've got a problem. So our alternate is the mean is not equal to 8.1, anything but what we need it to be. We were told that we want to do this at a 1% level of significance, so alpha is 0.01. All right, and I've written down the test statistic we're going to use, but before we do that, we need to get our critical values. And let's just recall our critical values. Since this is a two-tailed test, first thing we want to do is take our 0.01 and divide it by 2. That's going to give us 0.005. So we're going to look up our critical values. Now, putting 0.005 in is going to give us a negative z-value. But this is a two-tailed test, so we're going to have two different z-values and two different rejection regions. So let's go ahead first and look up 0.005. So I'm going to do equal norm.s.inv 0.005, and that gives me negative 2.576. All right, so our z-value for our critical values is negative 2.576, and then the other tail will be positive 2.576. So here's the idea in a picture. It's two-tailed. We have negative 2.576 here on the left and positive 2.576 on the right. Two rejection regions. So when we do our test statistic in a minute, if we get a number that's to the left of negative 2.576 in this blue area here, we're going to reject the null hypothesis. And if we get anything to the right of positive 2.576 over here, we're going to reject the null hypothesis. So anything in both rejection regions, we reject the null hypothesis. So let's go back. And let's actually now do our test statistic. And here's our formula for test statistic. Now, when we have the population standard deviation, as we do in this example, we want to use it. We didn't do it in example 4 because we are actually talking about another drug rather than the drug that made our initial null hypothesis. So that was not the population standard deviation for the drug that we were looking at for our alternate. Okay, so let's fill in to this formula and get our test statistic. So our X bar, if we look back at our example, our population, or rather our sample mean is 8.2. So we're going to go 8.2 minus our hypothesized mean of 8.1. Our standard deviation, and in this instance, since we have the population standard deviation, we're going to use it. And it told us, regardless of the mean amount dispensed, the standard deviation of the amount dispensed is always 0.22. So we're going to use that. with 30 as our sample size. So we're 0.22 divided by the square root of 30. And let's stick this into our calculator. The top's going to give us 0.1, and the bottom gives us 0.040166. And then if I go ahead and divide that out, rounding to 3 decimal places, I have 2.490. All right, so let's look back at our picture here. 2.490. If we look at our picture, well, it's not over here in the rejection region. It is, in fact, over here somewhere where my little target thing is pointing. So it's not in the rejection region. So let's go back here. And let's state it's not in the rejection region. And if it's not in the rejection region, we fail to reject the null. And as I said before, we never say that we accept the null. We always say that we fail to reject the null. We don't, as the researcher does not want to accept the null. They always want to kind of reject and get rid of the null and prove whatever their alternate hypothesis is. So we say fail to reject the null. Now, in this particular case, it's a good thing because it means that machine is not underfilling or overfilling. Most of the time, it's not a good thing when you fail to reject the null. All right, so once we've decided that we're going to fail to reject the null, we have to make a final conclusion. So there is not enough evidence, and we can state our alpha equals 0.01 to reject the null hypothesis. In this instance, since we can't reject it, we cannot say that there is a problem, which is really good in this instance. It appears that the machine does not presently need to be recalibrated. It appears to be properly filling the jars. All right, and there we have it.